And before we start, I introduce the committee. So we have maybe seen already in the morning by the talk from University of Bonn, Vincent Ph.D. We have then from the computer science, Andreas Weber, and also our external referee from actually plant science, so really external, Gabriel Schaaf. So we're now looking forward for the talk.
Welcome everyone to my PhD defense talk, and today I will be presenting an overview of my PhD research, which is about human pose estimation from unconstrained images and videos. So, so the obvious first question is that why we would like to do that? The answer is that our body is the way we interact with the environment. We use it for functional tasks such as for transport and manipulation, as well as to express ourselves. Even if we do not speak, our body convey a lot of information such as our activity, our mood, or the intent. For example, if we look here at Angela Merkel, we can all effortlessly understand that she is trying to hear or think something. And if we can develop computational methods with similar capabilities, they can be useful, for example, for robots, so they can naturally interact with other humans, for self-driving cars, so they can understand the pedestrians or cyclists around them. A good example of this is the zebra crossings, where we ourselves very often communicate with the car drivers and gesture that they can pass first. Similarly, for security and surveillance, where we can use such methods to detect suspicious activities. Another important application is elder care, where we can generate automatic alarm if we detect someone has fallen. For sports video analytics, it can be used to generate game statistics or provide personalized assistance to the players. Last but not the least, we can also use it in the gaming or entertainment industry to generate some visual effects or drive virtual characters based on our body movements. With so many practical applications and numerous others, the goal of my research was that given an unconstrained image or video, we would like to estimate the pose of every person visible in this image. And by unconstrained, I mean that we do not make any assumption on the number of persons in the image or the environment in which it is captured. And if it is a video, then we would also like to track the poses over time. Many applications such as robotics, they also need to understand that how far are the body joints with respect to each other, or how far they are from the camera. Therefore, we would also like to understand the 3D pose of the person. While the location of the wrist joint may be sufficient for many applications, our hands are the way we interact with objects. Therefore, we also want to understand the pose, the 2D and 3D pose of the hand in further details. In order to address these problems, we propose a number of approaches. However, in this talk, due to time limitations, I will be just presenting 2 approaches today. So the talk will be divided into 2 parts. The first part is about 2D pose estimation, and the second part is about 3D pose estimation. So let's talk about 2D pose estimation. Given an image with multiple people who can be potentially occluded or truncated, the existing approaches to perform multi-person pose estimation in images can be categorized into 2 types. The first type is the top-down method, which adopts a very simple approach and applies an off-the-shelf person detector to detect all the persons and pass each person to a single person pose estimation model to estimate the pose of each person. Where a single person pose estimation generally consists of a fully convolutional neural network, which takes an image of a pre-localized person as input and generates a set of heat maps, where each heat map provides the likelihood of the presence of a particular joint at every pixel location. For example, here in this image, this red region shows that these pixels belong to the right elbow of a person. In order to do the pose estimation, we simply go over all the heat maps, pick the pixel locations with the highest likelihood, which gives us the pose of the person. The second type is the bottom-up method, and these methods, instead of passing each person individually to the fully convolutional model, they pass the entire image to the model. This gives us multiple peaks for different body joints, which are represented here by different colors. Now we cannot simply go and pick the location with the highest likelihood, since there are multiple peaks. So what they do is they apply non-maximum suppression on those heat maps and generate a set of body joint candidates. Now we are able to detect all those body joints here, but we still need to know that to which person each of these body joints belongs to. This is a problem that we generally call joint-to-person association. This is generally formulated as a graph optimization problem, where we want to partition the graph such that each partition belongs to a separate, to the pose of an individual person. While both of these approaches can now estimate the pose of multiple persons in images, none of these approaches is directly applicable on video data. For example, this is the output of the most famous, commonly used approach for multi-person pose estimation in images. And we can see that here, due to color jittering, or in other words, due to identity switches, these poses are not very useful for us in video data because we do not know where each person is moving in the next frame. And ideally, what we want to have is something like this, where we assign a unique identity to each person, which is represented here with a different color. This means that we need to do pose estimation and tracking jointly for all the persons. When we started working on this problem, the first challenge for us was that there was no data set available for this. Hence, we started by proposing a new data set, which we called post-track data set. And in 2016, we started with 60 videos, and over time, we evolved to more than 1,300 videos, and to date, it has more than 260K pose annotations. On top of that, in order to attract the attention of other people towards this problem, we also organized two challenges, one at ICCV 17 and the other one at ECCV 18, and this is how the videos look like. So for each person, we annotate its pose, we assign it a unique identity over time, and the videos were selected such that they capture some real complex and challenging scenes, as we can see here. Given the data set, we also proposed the first method to address this problem. And for this, we adopted a bottom-up approach, and we generated a set of joint detections at each frame. The fully convolutional model used here to generate those joint candidates doesn't matter, and we can simply use any state-of-the-art method and plug it in the pipeline. Now, given those joint detection candidates, we need to associate each of them to a specific person within a frame and also across the frame. Hence, we are looking for the joint detections that belong to the same person in the entire video. This can be formulated as a graph structure, where the nodes of the graph are corresponds to these detections. And the edges formulate the relationship between these detections. Here we have two different kind of graph. The first one is a spatial graph, which connects all the detections inside the frame with all the detections with all the other detections visible in this frame. So the spatial graph is then constructed as the union of all those due subgraphs, and this will be responsible for the pose estimation part of the approach. The second graph is the temporal graph that connects the body joint detection candidates over frame. But one important thing to note here is that in this case, we do not connect body joint of different types across frame, but only connect body joints of same type over frame. And these edges are not only between the neighboring frames, but also across a fixed number of frames, so we can also handle some short-term occlusions or truncations. Once we have built the temporal graph, in order to solve multi-person pose estimation and tracking jointly, we take the union of both graphs and build a large spatiotemporal graph. Now we seek to partition this graph such that each partition of the graph corresponds to the tracked poses of an individual person. In order to do that, we introduce a set of binary random variables, where each binary random variable implies whether a particular joint will be part of the final solution or not. We also define an objective function which associates a cost to each of the binary random variables. And since we are minimizing this cost, we are looking for the nodes and edges that in the end minimize the overall cost of the objective function. So the cost for the nodes is defined by the probability of the joint detections, and since we are minimizing this cost, we convert the probability of each joint detection to a cost by this logit function, which converts it in such a way that a higher probability means a lower cost in the end. The cost for the spatial binary potentials is also defined in the same way. Same way here, the probability P of S corresponds to the likelihood that two different detections inside a frame belongs to the same person or not. For example, this head or head. Here we have, so this is basically the case where, so it has two cases. The first one is when both detections are of same joint type. And in this case, since we know that a person cannot have two heads. So in this case, we do not want to connect two detections until unless they are very close to each other. And in order to obtain a measure of closeness, we simply extend these detections to bounding boxes and compute those probabilities P of S as the intersection over union of these bounding boxes. And this gives us the probabilities. The other case is when both detections belong to different joint types, for example, a head and a shoulder. In this case, we utilize our prior knowledge. For example, we know that a shoulder is likely going to appear somewhere below the head. And this can be represented as the offset between the location of both joints. So we compute the offset between the location of both joints and put it as one feature. Similarly, we know that a head and a shoulder cannot appear very far from each other. Therefore, we also compute a distance between both of these detections and compute it as an additional feature here. Now, once we have the features, we need to obtain the probabilities, and we map these features to probabilities using logistic regressors, where these logistic regressors are learned in an offline fashion using the training data. Now the last cost is the temporal binary potential, and in this case, this probability P of T corresponds to the likelihood that two detections belong to the same person over time. For example, we want to know whether this detection in the next frame, this detection and this detection are the same or not. In order to compute this similarity, we compute dense correspondences between both frames and measure how many correspondences they share, both of these bounding boxes share. This can be seen as how much the color of these correspondences is similar. We compute a number of features based on those correspondences and again map them to probabilities using logistic regressors. Once we have defined all those potentials, technically we are ready to optimize the objective function. However, if we look closely at the behavior of our cost function, we will see that the cost of our the result of this cost function is positive whenever the probability P is lesser than 0.5, and it is negative whenever the probability P of P is greater than 0.5. So this means all those nodes or edges that have corresponding probability greater than 0.5 will be part of the solution because they overall minimize the cost, and none of the edges that have probability lesser than 0.5 will be part of the final solution. This can lead to implausible poses. For example, like this, where a person has two heads. For example, if we look at the location of these two heads with respect to the location of this shoulder, they both are at a relatively reasonable location with respect to this shoulder, and it is likely that both of these edges have a probability greater than 0.5. And this is something that we do not want. And in order to avoid that, we need to add some additional constraints to our objective function, which are the transitivity constraint. And we say that, okay, if two detections share a common detection with each other, then these two detections should also be connected with each other. This means that in order to add this edge in our final solution, the optimizer will have to pay a very high cost, and hence it will try to avoid adding this edge. Moreover, we can also lead to a situation where two detections, for example, this head and this hip detection, is spatially connected with each other, and both of them are connected with two other detections in the next frame. Now, since we do not add the temporal edges between joint detections of different type, we cannot enforce the transitivity constraints that I have presented in the last slide. This can lead to some solutions where the upper body of this person is connected to the upper body of one person in the next frame, and then the lower body of this person is connected to the lower body of another person in the next frame, maybe due to the similarity of the hip joints. This is again something that we know that a person cannot split over two frames. In order to avoid these cases, we add some additional constraints that say that if this is the scenario, then this green edge should also be added. Again, the optimizer will have to pay a very high cost in order to add this edge, and it will eventually avoid this edge. On the other hand, such an edge will be preferred. So once we have defined all our edges and all our costs, we are now ready to optimize the function. And since the objective function itself is linear, all the constraints that we add in the problem are also linear and the involved variables are binary, we can formulate the problem as an integer linear program whose feasible solution looks something like this. So here each partition of this graph is represented with a different color. And here is actually a bit better representation of the poses. And now we can see that we are now able to track all the persons over time. We are able to estimate their pose over time. And we can also handle variable number of persons in each frame, while we can also handle a variable number of, for example, for this purple person, variable number of visible body joints in each frame. And it can, of course, also handle very strong occlusions and truncations. Here we have some qualitative results. We can see that the model is now able to handle very large camera and person movements, some complex articulations, and fast person movements. While these were some qualitative results, we also compare our method with quantitatively with the approaches that were submitted to ICCV to the post-track challenge at ICCV 17, and all those are the approaches that were proposed after our method. And here the performance is evaluated in terms of MOTA visual multi-object tracking accuracy, which measures how well each joint is being tracked in the video, and we have sorted the performance of we have sorted the videos based on their MOTA accuracy. So post-track is our approach. ProTracker was the winning entry of this ICCV 17, and we can see that PostTracker in this dark red color, it performs pretty much competitive to other methods, and it served as a very strong baseline for all of those. However, the main takeaway from this approach is that we can see a very nice pattern here. For example, if we look at the first half of this plot, almost all of the approaches listed here perform very well on the first half, first part of the graph. On the other hand, almost all the methods fail very badly at the later half of the graph. So this means that these videos are the ones that are the really challenging videos, which gives us some nice future directions. For example, one of the most challenging situation is when the camera is moving very fast or the person is moving very fast. So such kind of cases require us to model the video data a bit more nicely. For example, in order to estimate the pose of this person, we need to exploit the information from neighboring frames. So from neighboring frames where this person was visible. Another case is of very rare poses, or when the persons occlude very strongly, when the persons are occluded very strongly. In this case, first problem is that such kind of rare poses also happen very rarely in the training data. Hence, either we need to increase our training data with more rare poses, or we need to come up with some more nice strategies for hard negative mining to address these cases. One more interesting case is of cases of people in large crowd who are very close to each other. In this case, we often miss the people who are visible in very small portions. So these are the cases which are basically also not encouraged during training. For example, these kind of persons contribute very less to the loss even during training. This means that we also need to come up with some nice training strategies so that we are also able to train some more stronger spatial models which can detect people who are very strongly occluded. Alright, so this was the first part of the talk, which was about a multi-person 2D pose estimation. And here I presented the first method to solve the problems of multi-person pose estimation and tracking jointly, and also I briefly explained the post-track data set, which is the largest data set for this task at the moment. So the second part of the talk is about 3D pose estimation. 3D pose estimation is an ill-posed problem, and what do I mean by that is that consider a camera model and a scene enclosed in its field of view. Now, this scene will have a particular 2D projection on the image plane of the camera. If I simply scale this scene and move it far from the camera, it will still have an exactly same 2D projection on the image plane. This means that just by looking at a 2D image, we can never reconstruct the 3D pose of a person. And in order to address this problem, what state-of-the-art methods do is that they adopt learning-based approaches. Given an input image, they train a CNN model which produces the 3D pose of the person. However, in order to reduce this depth and scale ambiguity, they always estimate the relative pose of the person, which means that we never know how far is the person with respect to the camera. All we know is that how the joints appears with respect to each other. Moreover, since these CNN models have to be trained, we need training data. And collecting training data with accurate 3D pose annotations requires very sophisticated hardware setup. And it can only be done in very controlled indoor environments. On the other hand, annotating unconstrained images with accurate 3D poses is infeasible. This means that if we just use this training data to train the CNN model, these models cannot generalize to unconstrained scenes. In order to address this problem, some methods try to lift the 2D pose directly to 3D. This has the advantage that since we can estimate 2D pose from any unconstrained image, as done in the previous part of the talk, we can actually then also estimate 3D pose for those images. However, this has one very severe limitation, which is that it cannot handle reprojection ambiguities. By that I mean that given this 2D pose, if we look at this as humans, even we cannot tell whether for this 2D pose the person is looking toward the camera or away from the camera. And we have to look at the image content to distinguish that. Why? So this means that if we directly try to estimate the 3D pose, it is prone to overfitting, and we can also not estimate the absolute pose of the person. And if we go to a 2D pose, then it cannot handle reprojection ambiguity. In order to address these issues, we propose a new pose representation that we call 2.5D pose representation. It has several advantages. First of all, it is invariant to 3D scale and translation. This means that it is much more less ambiguous than directly estimating the 3D pose of the person. The second thing is that in contrast to only 2D pose, it also contains some cues about the 3D pose. This means it can also efficiently handle the reprojection ambiguities in the pose. The third case is that since it contains 2D pose and some part of the 3D, we can also utilize multiple sources of training data, and which eventually allows us to generalize this approach to unconstrained images. And last but most importantly, it also allows us to reconstruct the absolute 3D pose of the person up to a scaling factor. And then we can approximate the scale if we know the height, if we know some priors about the size of the person. So let's see what is this 2.5D pose representation. So here again we have a perspective camera model, and here this capital X, capital Y, and ZK are 3D coordinates. With this camera parameter, they are projected to 2D. These are the 2D coordinates of the camera. We can write these 3D coordinates of a particular joint in terms of relative depth, where Z root is the depth of a particular joint, a particular root joint, which in case of body pose is generally the torso of the person. And then we can define the depths of all other joints with respect to this joint, for example, which are basically the relative depth of each of the body joint. Given this definition, we can write our 2.5D pose representation like this, where the X and Y axis is defined on the image plane, and the Z axis is defined on the Z axis of the camera, but it is relative, which means that this representation is independent of the 3D position of the person. Wherever the person moves, this representation will always remain same. However, we still have one more problem here, that it is still dependent on the scale. For example, a larger person will likely have larger relative depth as compared to a smaller person who will have smaller. And this is again something that we cannot estimate from only an RGB image. In order to remove this scaling information from this 2.5D representation, we scale normalize all the 3D poses, such that a particular region of the body, for example, the distance between the torso and the pelvis of the body, has a fixed length C. This means that if the person was bigger, its pose will become smaller, and if it was smaller, then its pose will become bigger. And in other words, we can say that we are rescaling the pose such that now this distance between the torso and pelvis is equal to C. This Z root is not the original Z root anymore, it is the scale normalized Z root, and then eventually these relative depths, they are also scale normalized relative depths. Now if we rewrite again this 2.5D representation in terms of relative depths, this representation is independent of the translation of the 3D position of the person as well as the scale. And this means this is much more easier to be estimated from a single RGB image. We can actually use any CNN model which takes as input an image of a person and provides us the 2.5D representation. Here, this is the 2D pose, and these are the relative depths. Since the pose is decomposed into two parts, we can utilize two different sources of training data here, where in each batch, we can take some samples from this source, some samples from this source. Whenever a sample comes from this source, which has only 2D pose annotations, but for unconstrained images, in this case, we only compute the loss for the 2D part and backpropagate through that. However, and on the other hand, whenever the sample comes from this source, which has accurate 3D pose annotations, this means we can compute both of the losses here and backpropagate through the entire loss. In such a mixed training setup, the network is then eventually also able to generalize to unconstrained scenarios. Now comes the point: what is the right CNN that we should use? The commonly adopted network is the ResNet model, followed by an FC layer, which then produces the 2.5D pose. However, ResNet has a limitation that it has a very high effective stride size, which means that it loses a lot of its spatial resolution by the time it generates the pose. This results in poses which has very sufficiently well articulation, but this kind of network can suffer to pinpoint the poses on the images. Therefore, the 2D pose community always relies on the heat maps, which basically retain the spatial resolution and hence are more better in accurately localizing the pose of the person in the image. However, this also has a limitation that it requires, in order to get our final 2.5D pose, it requires us to apply arcmax, which is non-differentiable. Therefore, we do not optimize for our end goal. We always optimize for the heat maps. Another limitation of this is that all of the body parts since these heat maps are hand defined, all of the body parts are considered as same. On the other hand, ideally, what we want is that the wrists for the heat maps for the wrists are very pinpoint, in contrast to torso, which even if they are a bit wide, it is fine for us. In order to achieve this functionality, we also propose a new CNN architecture, which takes an image as input and processes it through an encoder-decoder network and produces a two sets of maps. We take these latent 2D heat maps, process them with softmax normalization, where this parameter beta controls the spread of the heat maps, that how wide those heat maps should be, and then we apply arcmax soft arcmax on it, which gives us a 2D pose here. In other words, what we are asking is that generate me some maps here such that when I apply the softmax normalization, multiply it with a 2D grid, and take the linear combination of this 2D grid, it should result into the coordinates of my joints. This gives us the 2D pose here, and in order to get the relative depths, just imagine that we had the original depth map here, and it was our ideal heat map, which was a delta function at the exact location of the joint. What we would do in order to get the depth from that depth map, we will simply multiply this delta function with the depth map and take the sum, which will give us the exact depth at the location of the joint. We do exactly the same here. We simply take those heat maps, multiply them with this latent depth map, and take the sum, which gives us the relative depth. Since all of these operations are completely differentiable, we can apply the loss at the end of the network, and this gives us a heat map which look like this. Here we can see that the heat map for the torso is a bit wide. On the other hand, torso for the heat map for the wrist or the feet are very pinpoint, they are very precise. So now comes the point of inference. During testing, when we need to estimate, we need to reconstruct the 3D pose out of this 2.5D representation. This is what we get from the network. This is again the formula for the perspective projection. We can again rewrite it in terms of relative depth. In this equation, we know everything except z root. In general, we can plug in any value of z root here to obtain our 3D pose. But in our case, we know that the 3D pose that we are looking should justify this constraint, that the distance between the torso and the pelvis is equal to c. We simply rewrite it in terms of 3D coordinates, and it gives us the numerical solution to obtain the actual z root that we are looking for. We compute this value of z root, plug it back in this equation, and we get our 3D pose. All we are missing is the scale. And the scale we simply recover based on the mean pose of the data set that we obtained from the training data. And here what we are saying, mu KL is the mean limb length that we obtained from the training data. And here we are seeking for the scale S, such that when we scale the limbs of our scale normalized estimated pose, they should be as close as possible to the mean pose. And this is how we reconstruct our 3D pose. Here we have some qualitative results, and we can see that now we are able to estimate the absolute pose of the person, and we know that how far or how close it is from the camera. Some results on some unconstrained videos. We also evaluated this method on human 3.6 million. These blue bars are the ones from the state of the art. This is our method when we use only the data from constrained setups, and when we add annotations from unconstrained, we add unconstrained 2D pose annotation, it further decreases the performance. It further decreases the error, in this case, which is the 3D joint error. And we can actually apply exactly the same model also to estimate the hand poses, which we were also looking for. And this is how the qualitative results look like for the hand pose. Here we have some egocentric views, some first-person views, and some complex articulation of the hand. Some unconstrained images taken from the wild, and here we are seeing this 3D pose of the hand from different views, and some nice practical applications. And one interesting thing is that we can also use exactly the same model also to localize the key points of the face of the person. While we are seeing that, okay, now I am showing the poses of multiple hands here. Under the hood, basically, it is just a model for single hand pose estimation. So it is just detecting the hand separately and estimating the pose for those. So one of the interesting future work is to basically also handle cases where we have multiple interacting people. For example, here, whenever the hands get close to each other, the model starts to fail. So this is one interesting future direction. And while I am also showing basically the face and the hands in this video jointly, they are again estimated separately. So one of the interesting future direction is also to estimate the pose of the body, of the face, of the hands within a single model. And so far we also do not model the activity of the person or their interaction with the objects. So this is also one interesting future direction. In conclusion, I presented two approaches. One was the first method for joint multi-person pose estimation and tracking, and then the other was a model to estimate the absolute pose of the person from unconstrained images. That's it from my side. Thank you.
So we have no time while the piano is playing. For 50 minutes from the public audience. The committee can also ask questions, but they will also have later time. Are there any questions from the public audience? Yeah, let's start here.
Yeah, first question regarding your hand poses. So when you deal with hands, you are mostly interested in interactions, what are hands doing with objects, what are they touching, and when you just have like the pose coordinates, you do not really see when hands are touching. So what is the benefit of estimating the hand pose rather than estimating the actual hand shapes and its surface?
Yeah, so it depends actually again on the application. So in this case, if for example you need to do sign language recognition, in this case all you need is the articulation of the hands. Right. On the other hand, if you are modeling some interaction with the objects and you really need to know when exactly basically you have picked the hand, in that case you may need some hand models which also provide you the entire shape of the hand. So in this case, basically it really exactly depends on the application.
Any other questions? Yeah.
From 2D to 3D, where you like had a 2D skeleton and estimate the 3D skeleton, you said we don't know in which direction the person is facing, right?
Mm-hmm.
But we know that, right? Because the 2D estimation gives you left or right hand.
Exactly, but yeah, so maybe I should have a better basically visualization. But for example, in this exact image, the hand of the lady is at the back side, right? And this is something that we do not know then, right? So whether it is in front of the hand, like of the person, or at the back. So this is something that we need to know, in this case, and we need to look at the image for.
Any other questions?
Yeah, when you did the tracking, how did you compute these correspondences?
So it is basically, it was an off-the-shelf method called deep matching. All it does is that it passes the two images to the same model, and then is a simple basically L2 norm between the embeddings of both images, right? So it gives you how basically how similar they are, and then they do some extra processing of it to find out which are the right correspondences. For example, two-way check that this match is also matched to the first frame, and from the first frame it is also matched to this pixel in the second frame. So basically they do some additional processing to find out these correspondence.
Yeah. Can you go back to slide 60, I guess? Yeah, right. So in this architecture, you approximate the argmax function by a softmax function, if I got you right, which is very similar to what like recent approaches in key value attention, for example, would also do. And I'm wondering a bit because like one property of these softmax approximations is usually that you're really that you get a really smooth probability distribution. So you get kind of far away from the actual argmax you're interested in. Is there some implication? Is this an issue? Do you need to incorporate the temperature and the softmax during training to get it sharp enough?
Yeah, so here basically, if we just go to the previous slide, so this beta parameter is basically what controls the temperature of the softmax behavior, right?
Do you keep it constant? Or
No, we keep it basically learnable. So in
Okay.
the end, this is basically how it achieves this property of having different temperature for each body part. So this beta is basically a parameter for each body part. This
Mhm.
means this will be different for each of the body part. And then the resulting, the behavior of the softmax normalization will be different for each of the person, or each of the body giants.
So do you have a concrete schedule to increase or decrease the temperature during training, or is it just that during training you will also, among with all network parameters,
Exactly,
you
yeah.
will estimate the beta?
Exactly. Yeah.
But then the beta could also be directly put into the network weights, couldn't it?
Yeah. So basically, it is in the network weights. So
Oh,
basically, it's part
so-
of the network when we train it, along with.
Oh
all
no, I
the
mean
different-
like I mean you could factorize that. E to the beta k times e to the h blah blah blah.
Mhm.
And then you could essentially cross out the beta k out of this part, or am I wrong? So it's just a constant scaling that could also be directly in the weights of the network, couldn't it?
No, because he's saying that maybe P, the network that produces P, learns the beta
Yeah.
intrinsically.
In the weights, because you just have like this or maybe you can comment on what HK
So
to
HK,
D actually is.
HK is this map, right? These are
Yeah.
maps that are generated here,
Yeah.
and then you simply apply this operation on those maps.
Okay,
This
so the
particular
output
data.
of HK is not the output of the last part of HK. It's
No,
not
it
a
is
linear
not, no.
operation, but there is a nonlinear operation
Exactly.
as last part of
Exactly.
HK. Okay, then I see the point. Okay.
Any other questions? Yeah?
I have a question about whether there is already the software about the last work you mentioned about to get the 2D image or video as the input, and then you get take out the 3D pose sketch.
So
Is that already available online?
the code, no, unfortunately, no. But
Okay.
so you mean the code, whether the code is available or not?
I mean whether the code or you have some data set.
No, actually, for this one, there is nothing which is available online. For the first part, everything is available. For the second part, not. So this was part of my industry internship, so they just keep everything.
Oh, okay.
But if you need any help regarding implementing this or something, it is actually pretty simple to implement on PyTorch.
So any other questions? Yeah?
How fast is this graph optimization that you do in both
So at
association?
the moment it takes roughly 15 seconds. So we did some numbers. If I remember correctly, it was like only the optimization part, apart from running the CNN model and everything, only the optimization part was taking roughly 12 to 15 seconds per frame.
Yeah, I assume the CNN was something in the milliseconds.
It depends on which resolution you operate. For example, most of the videos in post-type datasets are very high resolution. And then in order to do pose estimation, you generally run it on multiple scales. So if it is basically an HD HD image with 1920 cross 180, and if you also want to detect smaller persons, you generally also upscale it by 2 times. So if this is the case, then sometimes it is. What I mean is like it is probably not in millisecond, but in it depends how many scales you try to run.
And I assume your second approach, which does not involve any graph optimization, is much faster.
Yeah, this was basically we were able to get on this one like up to 50 FPS.
So, is there a way to make the first approach also fully convolutional?
So, yeah, they
get rid of the graph optimization.
So this was in this approach basically we use a complex graph optimization approach, but most recent, for example, OpenPose and all those methods they utilize a bit more simple graph matching approaches. So yes, there are ways to make it faster. It depends on what kind of potentials you are getting from the CNN. In our case, we were not, for example, learning those potentials to match whether these 2 joints belong to the same person or not in a CNN setup. So they were not extremely strong. So they were just computed based on some locations of the joints. On the other hand, what OpenPose does is it learns those from a CNN. They are much stronger, and in the end, any greedy matching approach also works for them. But yeah, we can actually also reduce the runtime of this one. For example, you see that we keep a very densely connected graph in each frame, which is kind of a little bit unnecessary as well, in a way that we do not need to connect the person at the left corner of the image with the person at the right corner of the image. So one can also introduce some heuristics to reduce the number of edges in the graph, which will eventually also reduce the complexity overall.
So we have time for one last question.
When you compute the cost for the spatial connections in the post-track paper, I mean, there you need this, you need these bounding boxes. I mean, it's actually a dumb question, but how do you estimate actually the bounding box size? Doesn't it depend on the scale of the person?
Yeah, so it basically, since we are at that point, we are just detecting the joints,
Okay.
so we do not know the scale of the
Yeah.
person. But we can somehow roughly estimate the scale of the person so the pose estimation models are always trained on a unit scale, right? So during training, we always normalize the persons to a fixed height and then train the model.
Okay.
And then during testing, we hope that we will rescale the testing image to multiple scales, and at some scale, it will fit our unit scale. So we basically pick the scale from that point where we get the highest likelihood for this joint detection. So and then this gives us some rough estimate of the scale, and we use a fixed size of the bounding box, and then you can actually do scale normalization based on this.
Okay, so if there's no urgent last question, I would then simply conclude this public discussion. Let's first thank the speaker. So this committee will now go downstairs where we have the income discussion, so everyone can stay there, but I think we make that announcement on the 2nd floor, and then afterwards there will be also some food on the 2nd floor. Okay.